So there are, in addition to neurons, there are 5 types of glial cells. Most people think of neurons when they think of the brain, but the role of glial cells is actually becoming increasingly important. So there's 5 types of glial cells. The first is this epididymal cell. Okay, and saying these is, you'll see me sort of struggle with these because typically I only say these words out loud maybe once or twice a year when I'm basically saying them to this class. So oftentimes they're not words that I have a whole lot of practice with. So this glial cell is sort of oval in shape, and it secretes cerebral spinal fluid. So you will need this glial cell in your spinal cord. This glial cell will also be in your ventricles. Then you have an astrocyte. Okay, this is star-shaped and symmetrical. This provides a lot of nutrition and support function. Okay, this is basically a neural scaffolding, and it also secretes a chemical that keeps neurons healthy and helps them heal if they're injured. So they provide a nice sort of framework for neurons to rest on. They also contribute to the blood-brain barrier, which we'll be talking about more. So these astrocytes would line up close together near neurons and basically prevent large chemicals or substances in the blood from passing through the blood, out of the bloodstream into the brain. Then you also have a microglial cell. These are small, okay, and they have primarily a defensive function. So they originate in the blood as an offshoot of the immune system. And what they do is they identify and they attach to foreign tissue. And I'll be talking about this a little bit in a second for a really neat little video on the role of glial cells in what happens when their behavior can actually go awry. So this microglial cell, it will identify foreign tissue to help isolate that foreign tissue and remove it so that it does not problematic. It's also thought that this might be involved in some autoimmune diseases and elements of cancer because, of course, it will identify tissue that isn't actually foreign as foreign and try to attack it. In terms of repair, it provides growth factors that aid in the repair of damaged tissue, and in this sense, it may be involved in Alzheimer's disease. Then you have the oligodendroglial cell, and this forms myelin around CNS axons in the brain and spinal cord. So this is really important because myelin is what helps neurons communicate very rapidly. So we'll be talking about this cell in greater length in subsequent chapters. And then you have a Schwann cell, wraps around peripheral nerves to form myelin. So these ones do peripheral nervous system, and this one, the oligodendroglial cells, do the central nervous system. And these also repair damage in the peripheral nervous system. So if a neuron is damaged in the peripheral nervous system, it can be repaired. But if a neuron is damaged in the central nervous system, it cannot. So one of the things that researchers are trying to investigate is why here but not there? Why can something be repaired in the peripheral nervous system, but it can't be in the central nervous system? So if they can figure it out, then you might be able to heal injuries that at one point in the spinal cord that at one point would result in paralysis, for example. Okay, so here is an example of the astrocyte. Here is a blood vessel, and it will help sort of attach itself around the blood vessel, provide these sort of barriers that right around these junctions here, so that if larger molecules want to leave the blood vessels, then they're prevented of doing so by these astrocyte end feet. Okay, and then so they basically sort of cover up along the edges and junctions within blood vessels, because blood vessels also are formed by other cells. So they'll take this sort of junction between cells and cover them up so that things can't escape from the blood vessels that shouldn't. Okay, so here's an example. There's a really great book out if you want to or have some sort of first-hand experiences on the role of the brain and behavior. This is a really fantastic, interesting book. And so you can we'll have a brief little video here, and then we'll talk about it afterwards. All right, so this is the story of the woman who wrote Brain on Fire. It's based upon her personal experiences. So she'll tell you a little bit about it here.
I was a reporter for the New York Post, and I had kind of strange behaviors. I started becoming psychotic, and I started to hallucinate. And ultimately, I was diagnosed with an autoimmune disorder.
You had an hallucination, for instance, where you thought your dad was an imposter. He was actually, it was somebody else dressed up as your dad.
Yes, I believe that he was turning into people to play tricks on me. And I also believe that I could age people with my mind, which sounds so bizarre saying it now, but I believed if I looked at someone, I can actually make them grow older. I was very violent, especially when I was in the hospital, especially towards the nursing staff. I actually kicked and punched them, and I tried to escape. I was very violent at that time as well.
Where did it start? Give us how this started unfolding.
It started so subtly. It started kind of, I just didn't feel like myself. I felt off one day, and I mean, everyone feels off one day. And, I thought my boyfriend was cheating on me. I was convinced of it. So I actually ripped through his things in search of this kind of imaginary evidence, and I didn't find it. But, other kind of strange kind of paranoid thoughts started to emerge, and I kind of believed that, I was bad at my job. I became lethargic. I became withdrawn. So kind of small things, but I just thought, I'm having a bad month.
Didn't you have a very, very vivid experience being, I think, driven to the hospital or something? Is there a story there?
Yes, on the way to the hospital, further along in the illness, I actually tried to jump out of a moving car to escape. I thought that basically, I believed that my parents were kind of taking me against my will, and I wanted to get out. And any means possible, I wanted to get out of that car. I was getting worse and worse, so I was sliding from psychosis and hallucination and kind of, violence to catatonia. So I became withdrawn. I mean, no emotional register. I could hardly speak. I couldn't read or write. And at that point, he asked me to draw a clock, which is a very bizarre thing to ask a 24-year-old because it's typically a test given to Alzheimer's and stroke patients.
She's talking about her doctor.
So he gave me a piece of paper,
clock.
And he asked me to draw a clock. And so I drew a circle, and the numbers I drew in all on the right side.
So all the numbers were crunched into the crunch. There was a left-sided neglect, and all the numbers were crunched into the left side.
That was the clue. They didn't know what was causing my brain to kind of malfunction in that way, but they knew, okay, this is not psychiatric at this point. It took about 6-7 months, first of all, for me to feel any sort of normalcy again and to return to work. But then that 6-7 months, I actually wanted to start learning about what had happened to me. I became kind of open to hearing those stories, whereas before, I didn't want to hear about it.
I read this book, and I would highly recommend it. And even my 11-year-old son read it, so it's really more interesting than technical. And so what ended up happening is that this woman, she had a very rare type of autoimmune disease, in which it's highly likely that her microglial cells, basically on one side of her brain, and so she drew the clock on the right-hand side, so all the numbers were on the right, and so everything that was on the left was missing. Well, the right side of the brain controls the left side of the body. We'll talk about this more later on. And so she, the whole right side of her brain was basically fighting itself. And what's highly likely is that some of the glial cells that have this immune system function that are really important for reducing the risk infection in your brain, that they basically turned on the neurons. And then they started attacking her own brain tissue. And so she went from having very unusual psychological disturbances to being unable to move and total lack of motivation. And it's really, really fascinating story. And happily, with a happy ending. Obviously, she's written a very, very interesting book afterwards. But it gives you some really interesting firsthand knowledge of the experiences of, here was a normal woman who went completely behaviorally awry. And all of this was as a result of her brain basically malfunctioning. So it gives a really nice example of the types of things that your brain is responsible for that you don't really realize until it goes wrong. All right, so when your brain is damaged, it takes on a characteristic look and certain specific things happen. So here, for example, shows how brain damage tends to register most with gray matter. So So here's a healthy brain right here, and here's somebody with advanced Alzheimer's disease. The primary connections still are present, but there's a huge deficit in the gray matter. And the gray matter is sort of the interconnectivity between neurons, the interlinking between neurons that enables sort of patterned activation to form. So this would represent a huge loss of knowledge. Here is an example of how your brain looks different after you have brain damage in the form of a stroke. There was bleeding into the brain here, and so all of the blood, it damaged the brain tissue. And so once it was damaged, it was scarred and it wasn't functioning, and glial cells will actually come in at this point and try to remove some of the damaged brain tissue, because damaged brain tissue has the capacity to begin seizures, so it's actually advantageous to have it gone. So some glial cells that help with immune function and sort of will also help with cleaning up damaged cells. But this here shows you this is the same person. So here's their left half, here's their left half, and here's their right half. The right half that they had the stroke on is really problematic, but then parts of their left half look very much normal. Here's an example then of, this is what you would get from magnetic resonance imaging scanner. Here's a normal brain, and here is someone that has frontal temporal dementia. See some of the white matter connectivity that's still there that you would see sort of right in here, but then all of the gray matter, okay, that where sort of the sort of higher order processing would take place is absent. So this person would have very problematic behaviors. The frontal lobes are highly responsible for retrieving memories, and so when someone has frontal temporal dementia, they have a lot of trouble, they have a loss of memory. And so while some of their memories may in fact still be physically present in terms of physically represented in other regions of the brain, if the frontal lobes are damaged, then you can lose that information just because you have trouble retrieving it. After damage, a neuron is going to try to repair itself. Okay, so this repair can occur in the peripheral nervous system, but it cannot occur to the same extent in the central nervous system. So when a peripheral axon is cut, the axon dies. Okay, and then what happens is the Schwannian cells that were surrounding it, that provided the myelination, they shrink and divide and they form glial cells that basically say like, okay, well, look, these are sort of like the breadcrumbs of where it used to be. Okay, so the neuron then will send out these little axon sprouts, and these axon sprouts will look for the Schwann cells and sort of where they divided, and then these Schwann cells will signal sort of like, okay, look, grow here, this is sort of the path that you used to follow. And once the axon sort of follows this path, then the Schwann cells will again sort of wrap around the axon to form myelin. You can, again, over time, return to function and have a rapid communication along the axon. So this is basic peripheral nervous system repair.